All right, here, just a reminder about orbital diagrams. What are they? How do we use them? All that fun stuff. So, let's get to it. Orbital diagrams are the ones that you've done before, where we're going to start off with using our electron configuration. For example, here's lithium, where we say that there are two s electrons in the 1s orbital, and there's one s electron in the 2s orbital, and we're just going to put them into boxes so that we can show how they actually fill in. Why is this important? For things like dealing with oxygen or nitrogen or anything where you have multiple choices where we can put electrons. Over here, we've got Hund's rule at its finest, where we say, hey, we've got two electrons. Where do they go? They're going into two different of our orbitals here. So this could be, for example, the px and the py that they're going into, and just putting one electron in there. So this hopefully is what you remember, is we're just showing where those electrons go. If we had to deal with d orbitals, we recognize there are 3, 4, 5 d orbitals. How many do we have for F? That's right, we had 1, 2, 3, 4, 5, 6, 7 to fit all 14 electrons. And that's all we're doing here. It's just now showing it graphically where these actually go. These will be useful when we're talking about bonding theory. So where are the electrons? Where do they go for molecules? So definitely we'll need to know how to do as we go forward. A couple other pieces of information we're going to want to have is just some definitions. Paramagnetic versus diamagnetic. And it's just definitions here. If we have at least one unpaired electron, we call it a paramagnetic, and that says that is attracted to magnetic fields. So things like boron, things like carbon, definitely attracted to a magnetic field. Whereas if we look something down here like neon, we see that all the electrons are paired. These are actually repelled by magnetic fields. They are not attracted. This will also be something we'll see when we start dealing with molecular orbital theory and making bonds, but for right now, it's just a little bit of definitions that we need to have. Last bit of nomenclature here we're going to have is ground versus excited states. So let's take a look at the examples of lithium and beryllium here. And here I'm showing their electron configurations and their orbital diagrams just like we would from normal. This is what we call the ground state. It's the lowest energy. That's what we're always representing. What we could represent, though, however, is what we call an excited state. And that is what we are doing down here below. In these excited states, notice that no longer do I have this electron in the 2s. I have promoted it to a higher energy orbital. In this case, it's a 2p now. So I have moved one electron to a higher energy, therefore it's an excited state. Down here with beryllium, I took one out of the 2s and moved it all the way over here to 3s. That's a different type of excited state. So basically all we're showing here is in a ground state, it's where we can have them into the lowest energy configurations, where the excited state is anything above that. All right, so in other words, these are low in energy, where these are high in energy. That's what we need to know here. All right, so that'll do us for orbital diagrams, very basic reminder things, but as always, if it's confusing, you got questions, things aren't quite meshing with you, give me a holler, we'll get it taken care of, we'll get you back on track, and until next time, be excellent to each other.